I kind of went through our notes and actually also the book. And so this is kind of a summary of the reactions that we've done in terms of adding a group to the ring, in terms of the side chain reactions, and then the organometallic reagents. And then I didn't write the mechanisms because we did that yesterday for nucleophilic aromatic substitution, and of course the chart that you just wrote for me. So that's kind of a summary right now. If you made your own, then you can check, you can kind of check against that. But those are the reactions that we've done this week. And is it a lot? Yeah, it is. So I tried to organize them as best I can. Again, whatever your system is in terms of organizing it, that's what you want to do. You know what I forgot though? I forgot the diazonium reactions. So those will be on Monday's test, but I didn't put them on here, so maybe I'll do that. Or you can do that. They're in 2 chapters ahead, but they're also in the notes that are in the folder. Okay, any questions over like what we've kind of been doing? That seems about 19 and 20 maybe is where we're at right now. Going into 20 today. So I would suggest doing those up to what we end at today, that those would be good ones to do before the exam. I've lost control of saying, do these problems on this day by the end of this week. I will look at your scores at the end of in a couple weeks. Now, the last time I did this, I said, oh, you're responsible for all the electronic homework problems by the end of the semester. Chegg got quite the workout because everybody waited until the last 3 days and then they just copied the answers down from Chegg. I do not believe that Chegg has the answers to Top Hat, but I don't know that. When I found out they had the answers for Sapling, I called Sapling who did I call? Yeah, I called Sapling and said, it wasn't a good conversation anyway. I didn't know why Sapling didn't own Chegg, since they were putting their answers online. And they were like, well, there's only so much we can do. And I go, no, my legal team would own Chegg right now. And just remember, you're not doing yourself any good by just copying the answers, but that doesn't work all the time with students, right? Because it's about getting stuff done efficiently. But if you do the problems, hopefully they end up here. So it would be the problems that we're up to, but I haven't put any of those scores in. I'll probably just wait till the end to put them in. And it'll probably turn out to be a disaster like it was before. They said, don't ever do that again. Okay, so questions. There was a question about what kind of group is this? Because in the problems, in the practice problems that are online, my written practice problems, there are groups on there that may not be part of the chart that you just wrote. And I did not go through the gory details of why groups are activating, how they're pushing electron density into the ring, how they're taking electron density out of the ring. And maybe I need to have a quick discussion about that in terms of where does a sulfonic acid group fit as to whether it's activating or deactivating. Does anybody have any gut instinct as to what this should be? And I know that in my notes there's a much more detailed that this is on there, but based on the structure of the groups that you just wrote, number 1 to 10, what does this kind of look like? No. In terms of whether this is activating or deactivating, and in the group in the chart of number 1 to number 10 that you just wrote, are there structures in here, numbers 1 through 10, that this sulfonic acid group may resemble? 10 has an N plus, so I would say not quite 10. 8, 9, 7. So carbonyl, C triple bond N, and NO2, because remember NO2 looks like this. So if we look at this S double bond O, that's going to look like each one of these. It kind of resembles, anyway, it resembles these 3 groups, because what do these 3 groups have in common? Number 1, they have a plus or delta positive carbon that is attached by a multiple bond to a negative or delta minus atom. And the same thing would be true for sulfur. Sulfur on the periodic table is less electronegative than oxygen, so it would be slightly positive, and the oxygens would be slightly negative. So in terms of it looking like other groups, it looks like those groups, which makes it deactivating. So this is a deactivating meta director. So that's how we would look at this and say, okay, what does it look like that's on our chart? And it looks like those 3 groups, because I will sometimes summarize those 3 groups as saying it's an X multiply bonded to a Y, where the X is delta positive and the Y is delta negative. And so anything that looks like that is going to be a deactivated meta director. And on the other hand, anything that has an atom with a lone pair on it, that's sort of a general structure for an activating ortho-para-director. And that formula fits O's and N's. And if you think about putting a halogen on the ring, so the halogen is more electronegative than the carbon in the ring. So what's happening is the halogen is withdrawing electron density from the ring, because it's more electronegative, and so that is, the halogens are deactivating the ring. But because the bromine has 3 lone pairs on it, it looks like this general structure of an orthopara director, and so that's why the bromine is an orthopara director, but it's withdrawing electron density because it has lone pairs. So the lone pairs, if the group is not withdrawing electron density tremendously, then it's an activating orthopara. But the bromine with the lone pairs look like an orthopara director.
If the group is activating and deactivating, does that require that like if it makes the reaction go slow?
Yes. So in your chart, the first 4 groups make the reaction go faster than benzene. Then there's benzene, and then the groups below benzene, 6 through 10, are all making the reaction go slower than benzene. So that's what activating and deactivating means. But 1 through 4 and 6 with the halogens are orthopara directors, and then it's 7 through 10 that are meta directors. So that's what the activating deactivating means. The question is it pushing electron density into the ring to be activating? Is it withdrawing electron density like this to be deactivating? So an SO3H group is deactivating meta. Now where it would fit on the chart, we're not going to worry about. So if I give you a reaction or a problem where you have to rank the groups on the chart, those are only going to be limited to the groups on the chart. But all carbonyls are the same. So I'm not making any distinction between an aldehyde, a ketone, or a carboxylic acid. They're all the same. All right. So were there any other? Maybe towards the end, maybe we'll go back and do some more of the how do you go from A to B to C kinds of problems. But the theme for today is aldehydes and ketones. So did anybody have any initial questions on aldehydes and ketones? So this is the first chapter on carbonyl chemistry, which quite honestly is probably the most important part of organic, because if you go on and take biochemistry, the kinds of molecules you're going to talk about are all carbonyl chemistry. But nobody writes a book where they put carbonyl chemistry in the first semester or at the beginning of the second semester. And when they've tried, nobody's bought their book. So they've gone bankrupt. So we always wait to do carbonyl chemistry at the end of the semester one would think it'd be fresh in everybody's mind, but at this point your mind's full of stuff. So we have to kind of make a little bit of room for this. And so what I usually talk about with aldehydes and ketones is why are we going to break the carbonyl chemistry up the way we're going to break it up. So in other words, there is one chapter just for aldehydes and ketones. So in this, I'm always going to assume there's an R group over here. So an aldehyde has an R and a hydrogen around the carbonyl. 2 R groups is the ketone. So it's ketone and then aldehyde. And just like when people write Friedel-Crafts reactions, and they use crafts like the cheese with a K, that's kind of like fingernails on a chalkboard. Ketone with a Y is like fingernails on a chalkboard. It's just Ketone. These make up one chapter. And then the next chapter after amines will be carboxylic acid chlorides, which we talked about with reacting Grignards with those. Then next are carboxylic acid anhydrides. Which we used in lab the other day to make an NH2 group into an amide. That's actually how we did it, was using the anhydride. Then we have a carboxylic acid. So we've got an R group with the C double bond O, OH. Then we have an ester. And then we have an amide. And the nitrogen could have one hydrogen, two hydrogens, one alkyl group or two alkyl groups, any combination. So that is called an amide. An amide, amide, amide. It's kind of sometimes difficult to know the difference between amide in this context and an N-, which is also called an amide. So these are the two classifications that we break carbonyl chemistry up into. Aldehydes and ketones, and then what are called carboxylic acid and its derivatives. And so when we get to this, which is going to be the second last topic of the semester, we're going to find that we can convert a carboxylic acid into every single one of these other compounds, and so that's why they're called derivatives. Actually, that's not the reason they're called derivatives. Carboxylic acid derivatives, when you react them with acid and water, they form a carboxylic acid. That's the true definition of a derivative. That when you hydrolyze it with acid and water, or base and water, you make a carboxylic acid. And I'm going to order them this way for reasons that I'll get to. But why do we break these two? Why do we break all these carbonyl chemistry up into two groups? It's all based on what kind of leaving group do we have attached to the carbonyl. And our classification here at the first level is, can that group leave? Not necessarily is it good or poor, but can it leave? And so far, when we've talked about leaving groups, well, review leaving group abilities based on uno thing, basicity, directly or indirectly? Indirectly, right? Strong base, poor leaving group, and vice versa. So if you take our top two bases, what are they? C- and H-. Have we done a reaction yet where we have kicked off an H or kicked off a C in a substitution reaction? No. I'll answer that for you. No, we haven't. And then I usually follow that up with a statement, okay, you're 65% of the way, 70% of the way through organic chemistry. You've seen how chaotic it is in terms of all the different reactions we've learned. How much more chaotic would it be if your skeleton, if your carbon-hydrogen skeleton that you're hanging functional groups off of, how chaotic would it be if you could just kick off a part of a chain or kick off a hydrogen in a substitution reaction? There would be no order to it at all. So the carbon-hydrogen chain, that is the skeleton on which we hang things off of. And so if those groups left, or were leaving groups, it would be a nightmare to learn organic chemistry. Okay. So however this was designed, those two groups never act as leaving groups. And so that's why they're on the left. Because I'm going to put those together because I cannot kick off a hydrogen or a carbon. All these other groups on the right, I can get rid of. In what kind of reaction? Well, here's the reaction that we're going to basically do, and I'm going to put a Y here. So let me add a nucleophile. Let me add a strong nucleophile. And so a strong nucleophile comes in, attacks the carbonyl, and we form the O- with now the Y group and the nucleophile group. This is an overall, just a very generic reaction. What happens next? When we talked about Grignard reactions, when I make that O-, what's that O- try to do first? Tries to come down and reform the double bond. Now, if it comes down and reforms the double bond, what has to happen? Something's got to get kicked off. Now, when we talk about the carboxylic acids and when we talk about aldehydes and ketones next, what we're going to find is oftentimes it's the nucleophile that goes. And so if the nucleophile goes, what happens? I go backwards into equilibrium. But if the Y group goes, then what do I end up doing? I end up losing my Y, and I end up reforming my carbonyl, and now what I've done is I've done a substitution on the carbonyl group. And this is sometimes called Acyl substitution. So the real question is, what happens? And then what happens if Y or the nucleophile can't leave? If neither one of these groups can leave, then the molecule just stuck there as an alkoxide waiting around to be protonated. And so then it sticks, you add H plus to it, and you make your alcohol. So we could go back to Grignards and reductions with aldehydes and ketones. And that's those are the perfect examples of where we either stick at the alkoxide, or when we reacted a Grignard with an acid chloride, or we reacted it with an ester, what happened? It would form an O-, the O- would come back down, kick off the chlorine, and the second Grignard would add. Or it would kick off the OR group and the second Grignard would add. So if you go back and remember what we did with Grignards, if it was an aldehyde or ketone, we're done. If it was an acid chloride or an ester, we could add a second equivalent because that pair of electrons would come back down, reform the carbonyl, and kick the other group off, and then the Grignard would add a second time. So we've done this in the past. And so this is why if I'm going to organize carbonyl chemistry, I'm going to organize it into these two classes: aldehydes and ketones, and then acids and their derivatives. And that's the point of classification. Can this group leave? Because I'm going to add stuff now to the carbonyl. And so when I add it to the carbonyl, the first thing the carbonyl O- is going to do is it's going to try and reform. And it's going to have to kick something off if it wants to do that. So that's the overall scheme. And that's why we organize the text this way. Okay. Does that kind of make sense? Because that's basically, this diagram right here is basically the next, well, it's the next 2 out of the 3 chapters. Because amines are always thrown in there in the middle to break it up. Okay. So let's talk about the aldehydes and ketones. And let's add nucleophiles to them. Okay, so if we have an aldehyde or a ketone, and I'm going to kind of write it like this, so it could be an H, could be an R group, could be an aldehyde, could be a ketone. What do we already know how to do with these? Because it's always best to start with review. I know that I can do this, right? I can add Grignards, and then H plus H2O to them. And what am I going to make? I'm going to add my R group, and I'm going to make a primary or a secondary or a tertiary alcohol, depending on whether I started with formaldehyde with 2 H's, an aldehyde with an R and an H, or a ketone with 2 R's. I'm going to make primary, secondary, tertiary alcohols by Grignards. Okay? We did that. We've done that. We could even go back to what the chapter we started with, and we could say, okay, I'm going to react my aldehyde or ketone with this alkynyl anion, then H plus H2O, and now I'm going to end up adding the C triple bond, the alkynyl anion. I mean, that's the first place we started with this. What other strong nucleophile can I add to the carbonyl? Well, I could add H minus and do reduction. What reagents did I use to do the reduction with? What gives me H minus? NaBH4 would be one of those, or aluminum hydride. So I could use sodium borohydride, lithium aluminum hydride, then H plus H2O. And now what I'm doing is now I'm reducing that down to the alcohol. But what did I end up adding? The H. And every single one of these mechanisms is exactly the same. The nucleophile comes in, attacks the carbonyl, we form the O-. The O- then tries to come back down, but there's nothing that can leave, so it gets stuck there and it just hangs out until it gets protonated. Right, if we want to give it personal characteristics. So what I know when I'm going to do this reaction of aldehydes and ketones is the two groups that I'm starting with aren't going anywhere. But, okay, these were great, strong nucleophiles. Now I want to broaden my nucleophile base out. And so now what do I want to add to these carbonyls and these aldehydes and ketones? Now I want to add water, alcohol, amines. I basically want to add neutral nucleophiles. And I'll just point out right now that all we're going to add is neutral nucleophiles. If you say, hey, how about hydroxide? Last chapter. Because when you start adding strong bases to this, it does a completely different reaction. So I'm just going to use neutral nucleophiles to do these reactions. Okay. So we'll do this with an aldehyde first. Well, no, we won't. A couple things before we start piling on reactions. Question. Let me put a third. Who's the most stable? A, B, or C? Somebody give me a letter. Give me another letter. Give me another letter. Which one is the most stable? B. I would probably ask why, but the fact that we went through A and C and finally got to B means that might not be an effective question. But why do you think B would be the most stable? It is the most substituted. So a carbon-oxygen double bond is no different than a carbon-carbon double bond in this case. So the more alkyl substituents, the more stable you are. So a ketone is not the more stable, it is most stable. And formaldehyde is the least stable. So we treat the stability of carbonyls the same way we treated the stability of alkenes. More alkyl groups, more stable. Right, so that we need to say up front. Ketones are more stable than aldehydes. Okay. And that's going to come into play in a couple of minutes. Now, what I would like to begin doing is adding neutral nucleophiles to this carbonyl. But I have a problem. Here's my problem. Even an aldehyde, even though it's not as stable as a ketone, and remember there's the stability reactivity principle in chemistry, right? The more stable you are, the less reactive. The less stable you are, the more reactive. Right? That's a chemistry/people principle. So this aldehyde, even though it's more reactive than a ketone, it's not that reactive. So if I try and add H2O to it, H2O is a weak nucleophile. It can't add to the carbonyl. It needs help. So it just cannot add on its own. So how do I give this carbonyl help? I'm going to add acid to it. Now, what happens when I add acid to this carbonyl? My first step is to Which O? Protonate the oxygen. I haven't said that enough this semester, but whenever we have an oxygen species and we add H plus to it, the first step is protonate the oxygen. So in this case, I'm going to protonate the carbonyl oxygen. And just if you're curious, well, why wouldn't you protonate the water? If I protonate the water's not a nucleophile anymore. So I need to protonate the carbonyl, and what do I make? I make the protonated carbonyl. How is that helping the carbonyl become more reactive, or how is that helping the water add to the carbonyl? Not from this, but from its resonance structure. All right, so its resonance structure, I take this pair of electrons, I give it to the oxygen, and I now have the oxygen being neutral, but now what have I done to the carbon? I have made it +1. But that carbon only has 3 bonds. At this point, it's like, okay, that means it's a carbocation. What's the real structure, though? The real structure isn't either of these two, it's the hybrid. And so if we wrote the structure of the hybrid, it would have a partial bond to the oxygen. There would be a delta plus on the oxygen and a delta plus on the carbon. So that would be our hybrid. So at this point, half of what we're doing is stuff we've done in the past. So let's review. So at this point, I would not be attempting to be an effective teacher if I didn't say, where have we done this in the past? We did something similar to this when we took our epoxide and we protonated the epoxide. What did that oxygen do? It pushed the positive charge down to the 2 carbons. So when I protonate the carbonyl oxygen, it pushes the positive charge down to the carbon. How does that help the oxygen out, or help the water out? Well, now the water, which is weak, is now seeing a stronger electrophile. And so if it sees a stronger electrophile, it'll be able to add to it. So you can add the water to either one of these 2 resonance structures. What I would do is I would say, okay, here's my protonated carbonyl. I would add the water to the carbon and move the pair of electrons up to the oxygen so that I'm going to make this species. If you wanted to take the protonated carbonyl, write its resonance structure, which is this one, write that resonance structure and then add the water directly to the carbocation, you can do that as well. It doesn't matter to me. But what I've done is by protonating the carbonyl, I've made that molecule a stronger electrophile so that now the water can add to it. And if I'm going to do this with weak nucleophiles, like water and alcohol, I need to protonate first. Sort of. So aldehydes and ketones need acid. I'll talk about formaldehyde in a minute. All right, so I just added the water to the carbonyl. Next step. Which one would you like to get rid of? So we're going to lose that H plus. How many times have we done that this year? Summer? How about more than once? Hopefully tens of times. Wouldn't be hundreds of times, but at least would be approaching 10. That we've made an oxonium ion and we've lost H+. And so we make this molecule. And this is called a hydrate. That's a hydrate molecule. Now, what's the role of the H+? I used it at the beginning, I generated it in the last step. The H+ is a catalyst. So what does that mean? That means that when you make your hydrate, what can happen? Either of the two oxygens of the hydrate could be protonated by the H+, and we would go backwards to the oxonium ion. The oxonium ion could leave as water, so we could go backwards. And so overall then, this reaction to form the hydrate is equilibrium. It's an equilibrium reaction. So if we were to write this hydrate reaction, we would say, I'm going to take my aldehyde or my ketone, react it with H2O, using H+ as a catalyst, and I'm going to form the hydrate and so that's going to be the overall reaction. So I make this hydrate. So because this is an equilibrium reaction, we do have an issue. And our issue is which side of the equilibrium, or which side of the equilibrium does it lie? So in other words, when I do this reaction with just some run-of-the-mill aldehyde and ketone, do I get more hydrate or more unreacted? And the answer is that hydrates, for the most part, are unstable, and so the equilibrium will lie to the left. In general. If this is just a run-of-the-mill aldehyde or ketone. If I want to push the equilibrium to the right, you might say use excess water, but that's not going to work. So now I have to think about, when we've talked about acid-base equilibria, and I want to push the equilibrium to the right, and I can't use Le Chatelier's principle. What have I done to make an acid stronger? How have I pushed this equilibrium to the right? So that's Le Chatelier, and I can't do that here. That may make more H+, but relatively speaking, it's not going to change the equilibrium constant. What I usually do is make A- more stable. So if I make A- more stable, then what happens? The equilibrium moves to the right, we get a stronger acid. Can you give me an example of that? I can give you an example of that. The sulfonic acids that we just made are strong acids. which means that the sulfonates are weak bases, very weak, so that they actually aren't even bases. So in this case, that conjugate base is very stable. What makes it stable? All the resonance structures you can draw. So the fact that you can draw more resonance structures means that's going to be more stable, which means that is going to push the equilibrium to the right, which is going to make this a very strong acid. So remember, ring a bell. So I'm not going to use that principle. I'm going to use the reverse of that principle. I don't want to make the product more stable. I want to make the reactant less stable. So the more unstable I make the reactant, the more it's going to push to the right. So I can either push to the right by making the product on the right more stable, or I can push it to the right by making the reactant on the left more unstable. So how do I do that? Well, let's use the most unstable aldehyde we got. Formaldehyde. What do you use formaldehyde for? Preserving dead things. The problem is with formaldehyde is a gas, which is why you might hear about, like in new construction and stuff, or maybe even part of the new car smell of formaldehyde. Yeah. It's bad. But it's like everything else, it's concentration. I don't know, just stops mold from growing and stuff from decomposing. And formaldehyde is sort of like not in vogue anymore. You just use methanol. So formaldehyde being the most unstable aldehyde, its equilibrium will lie mostly to the right. So if you do want to make a stable hydrate, formaldehyde would be one of them that actually forms a stable hydrate, or the equilibrium lies to the right. For most of your run-of-the-mill aldehydes and ketones, the equilibrium lies to the left, except for formaldehyde. The equilibrium there lies to the right. And I can go one step further and say that I could actually turn any aldehyde or ketone into an unstable aldehyde or ketone by doing the following. I could take the carbon that's attached to the carbonyl, and I can attach 3 halogens. And I'll go moderate here by just using chlorines instead of fluorines. But what happens is if you add 3 chlorines to this, each one of those chlorines becomes negative. Where did it get its negative charge from? The carbon that it's attached to. So the carbon that it's attached to becomes really delta positive. But wait, what's the charge on the carbonyl carbon? The carbonyl carbon is delta positive. So if I put electron withdrawing groups like chlorines on the carbon next to the carbonyl, I now have created 2 carbons with delta positive charge. That is not a stable situation. And so when I react that molecule with water, the equilibrium will lie mostly to the right, So that now what I'll end up doing is forming that hydrate. And so this is called chloral. And this is called chloral hydrate. So those systems are also ones that you're pushing the equilibrium all the way to the right. So, but for the most part, aldehydes and ketones, when you add water to them, the equilibrium is going to lie to the left. They're going to form a little bit of hydrate, but not much. It's when you go to the extreme, like formaldehyde, or when you use chloral, that's when it's going to shift mostly to the right. So that's how we can make hydrates. Water, and actually chloral or formaldehyde, they don't need acid to do this reaction. So that's forming hydrates. So everybody kind of with me? Anybody bored? Kind of bored. Because now the reactions that I'm going to do are just basically the same ones over and over again. So I did water. What should I do next? Let's do alcohols. Let's add alcohols to ketones or aldehydes. So I'll just make it an aldehyde to begin with. All right, I still need H+. So let me add my H+ to my aldehyde. And I'm going to form my protonated aldehyde, and now I'm going to go ahead and add some generic alcohol to it. And what's going to happen? Pretty much. But what is that? Already did. Already protonated the oxygen, now what's next? I could write that resonance structure, and then what happens? The alcohol is going to attack the carbonyl. A pair of electrons will go up into the OH. That's going to be an equilibrium reaction, so then I'm going to form my, now I'm going to end up with my alcohol then adding to that carbon. And then what happens next? Lose the H off of the alcohol part. And so now I'm going to form a molecule so I lost my H+ to now form that. It's got an OH and an OR. Okay, what is that called? No. That'd be a carbonyl with the OR group. This is called a hemi, and then it's either a hemiacetal, or it could also be called a hemiketal. What's the difference? Did this come from an aldehyde, like in this case, or did it come from a ketone? So if it came from an aldehyde, it's an acetal. If it came from a ketone, it's a ketal. So hemiacetals and hemiketals have an OH and an OR attached to the same carbon. So, and I'll put an R prime in there for R1. So now I still have acid present. So if I wanted to, I could add a second equivalent of alcohol. Same alcohol or a different alcohol. Let's use the same alcohol. So now what's going to happen is my H plus is going to protonate something. That something being the OH or the OR. So what do you want to protonate? The OH. If I protonate the OR, what happens? I go back up. So I want to move forward, so I want to protonate the OH. So now I'm going to end up with an oxonium ion. What happens next? The water leaves. What happens next? I'll take another of those another one of those alcohols. So actually in this case I'm going to react acid as a catalyst and 2 ROHs. So now that alcohol is going to do what? It's going to come in and add to the carbonyl. So now I'm going to end up with the oxonium ion from the second alcohol adding. And then in the final step, lose the H plus. So in the end, what do I now have? I've got 2 OR groups attached to the carbon that was the carbonyl. H plus is still the catalyst. So if you add 1 equivalent of alcohol, you make a hemi. And I should have said, well, if there's a hemi, then that must mean there's, because hemi means what? Half. So if that's half of an acetal, there must be a full-blown acetal. That's your acetal. Or if I did this with a ketone and there was an R group here and another R group there, it would be a ketal. So the hemiacetal and the hemiketal are half of an acetal and half of a ketal. And so, and this is pretty tedious. But is there anything new here, stepwise? No. So to summarize that one, if you added the aldehyde or ketone to 1 equivalent of alcohol, you make the hemiacetal, hemiketal, and then if you add it to 2 alcohols, you're going to make the ketal or the acetal. Now the issue here is, where does the equilibrium lie? And just like with the hydrate, your run-of-the-mill acetals and ketals, the equilibrium is going to lie towards the aldehyde and ketone. But there are special things I can do to push this equilibrium to form the acetal or ketal 100%. The first thing I could do is do what I did before. Add chlorines, maybe use formaldehyde, and that would push the equilibrium all the way to the right. But the way that we normally push the equilibrium to the right is by using a dialcohol, so that we can make a cyclic acetal or ketal. And that's going to lead us into a little bit of a tangent. So I want to use a dialcohol that has two OHs attached to in the same molecule. This is called ethylene glycol. You could also use a 3-carbon, which would be called propylene glycol. Ethylene glycol is a commonly used dialcohol. With two OHs, it can hydrogen bond twice as much. That means ethylene glycol has a higher boiling point and a lower freezing point than like a normal alcohol would have. So when you add antifreeze or anti-boil over stuff to your radiator in your car, which, you know, who does that? The guy at the gas station, or Mr. Tire over here does that. Or if it runs really low like it did the other day, I had to do that, make my own pit stop in front of fill the tire thing, so somebody was tooting at me to get done. But we add this to our radiators to raise the boiling point or lower the freezing point of the water. And you have to be careful when you use ethylene glycol, which I was not the last time I filled mine because I didn't have a funnel. Because you don't want to spill it on your driveway, because ethylene glycol has a very sweet taste. Not to you, because you're not going to be licking it off the driveway, but animals will, small animals, and ethylene glycol is just a tad bit poisonous. So when you use this, you don't want to spill it on the ground, because then the small animals will come and lick it up and get poisoned eventually, if they lick up too much of it. But there is an environmentally friendly, and that's propylene glycol, which has 3 carbons. And it's not as poisonous as the ethylene glycol. It's more environmentally friendly, which adds to a principle in organic chemistry. I mean, just 1 carbon can make a huge difference in a molecule. But you might have already known that, because methanol with 1 carbon, you don't drink, or you go blind, or die. Ethanol, in moderation, doesn't make you go blind or die. So 1 carbon does make a huge difference in organic chemistry and in biochemistry. So ethylene glycol is what we use. We could use propylene glycol, but ethylene glycol seems to work. Yes. Because it depends on what the ethylene glycol metabolizes to when it gets in a system. So like methanol, if you oxidize methanol with 1 carbon, you're either going to make formaldehyde or you're going to make formic acid. Whereas if you're oxidizing ethanol, you're just making like acetic acid, which is vinegar. So we can ingest vinegar doesn't do anything to us. Don't know that we would want to ingest formic acid. We certainly wouldn't want to ingest formaldehyde. So it's the oxidation products, it's the metabolism. Metabolism is what makes something poisonous. And so that one carbon difference in the metabolite might be the difference. But you'll talk more about that if you go on and take biochemistry or molecular biology or whatever class you take. Okay, first step in this mechanism. Protonate the oxygen on the carbonyl. Second step.
Hannah.
You already answered.
Greg.
Greg, what are we going to do? Yep. So we'll take one of the oxygens and we'll attack the carbonyl with it, and we will now make our oxonium ion. And remember, you cannot split the OH apart. You've got to add the entire neutral nucleophile to make the oxonium ion. It's got free rotation.
Alex.
So what happens next, Alex? We're going to lose the H plus there. So for instance, I could write it like that too. I could write the ethylene glycol part like that. It's got free rotation, so it's okay. So now we're back. So we're back to there. So now what's the next step?
Megan.
Actually, I'm not going to add another ethylene glycol. I'm going to take this second OH and wrap it around. But before I do that, what do I need to do? No. What do I need to do with this OH? What did I do in the last step? In the last step, when I had my OH, what was the first step? I'm going to protonate this OH. So the next step is going to be to protonate this OH. So I acid my catalyst, so I still have H plus in there. So I'm now going to take my H plus, and I'm going to go ahead and add the H plus, or protonate now the OH. So I'm going to make an oxonium ion out of that. So if I protonate the other OH, it doesn't go anywhere, right? If I protonate this OH, water's not going to leave because then I got a primary carbocation. So if it protonates, then it's constantly back and forth. But when it hits this, when I protonate that OH there, now what's going to happen?
Aishwarya.
Not yet. Not lose water. I want to lose water. because what I'm going to end up adding to is, so I'm going to lose my water so that now I end up with a carbocation. And then I have my oxygen down here with my OH group. So I got to lose the water next. And so next I'm going to
Cameron.
Okay. So I'm going to wrap that OH group that was attached. That's the second OH group of the ethylene glycol is now going to wrap around. What I usually do at this point is I'll make them add to the same side, sort of the same face. So I would just wrap it around and add it. It's going to end up making a 5-membered ring. So I have an oxonium ion, and my final step is going to be
Panel.
wait, I thought it removed you. I thought it removed you. But what do you want to do? Just lose the H plus. So in the end here, what I'm going to end up making is I'm going to end up making a 5-membered ring with the 2 oxygens attached to the same carbon. So in this case, this is an acetal because it's 2 OR groups attached to the carbon. Now the fact that they're attached to each other is irrelevant, except that now I make what's called a cyclic acetal. And so when I make a cyclic acetal, it turns out that the equilibrium will now lie to the formation of that 5-membered ring. So when you want to make an acetal or a ketal and push the equilibrium to the right, you can use the tricks we used before. Formaldehyde, adding chlorines to the carbon next to the carbonyl. But the third way to push the equilibrium to the right is now use a dialcohol and make a cyclic acetal or a cyclic ketal. And so that's the third case where the equilibrium will lie to the right. So that would just be called now a cyclic acetal. So again, this is tedious. There's really not any new steps other than the fact that what I'm trying to do now is when I add the OH group from one side of the molecule, in the second step I'm going to add the OH from the other side of the molecule. And so now it wraps around and it makes the cyclic compound. So this is stable. So the mechanisms of adding the water with acid or adding the alcohol with acid is a mechanism that we can do. On Monday. Okay. Yeah, this is one of the cases where the equilibrium lies towards the product are pretty limited, and this is one of them. So when you react it with ethylene glycol, you make this acetal, and I could isolate this acetal, this cyclic acetal from solution. I could purify it. I could column chromatograph it. The only thing I can't do with it is have it touch acid and water, because if this now reacts with acid and water, the equilibrium, particularly excess water, the equilibrium will now go backwards, and I'll now go back to my original aldehyde. So this is stable as long as the solution is basic, as long as the solution is not acid and water. I can crystallize it, I can do all the things in lab that you can do with a molecule. But as soon as it touches acid and water, it's going backwards. So that was 3 whole reactions. But the rest of them are just going to kind of be little tweaks off this. All right, let's take our little break here. And then we're going to apply this reaction to sugars.
I'm all
Okay. So, you have seen at one point, you've seen hemiacetals or hemiketals if you've taken a biology class, because when you form sugars, you're actually forming hemiacetals or hemiketals. So this would be, and this is in the this is in the Canvas page for today. This is just a listing of all the different kind of aldoses and ketoses, which is something that I normally don't teach because that's biochemistry, and that somebody else takes care of. But a long time ago, I taught an introduction to biochemistry for like dietetics majors and engineers when I taught at OU. And so we always started with what kinds we had. And so then you've got your aldotrioses and tetraoses, etc. But here's the relevant part. The relevant part is that for glucose, for instance, or for fructose, for glucose, you have an open chain form where you have an aldehyde at the top, and I can't draw on that. So you have an aldehyde at the top, and it won't even point, it'll just move. So you have an aldehyde there at the top, and then the OH on carbon 5 is actually what's going to react with that aldehyde to form the hemiacetal. So when it happens, it forms a cyclic structure. So on the right, you see the Hallworth projection, which is in biology you usually notate rings as just planar 6-membered rings. We know that's not the case. We know they're cyclohexane. They're chair conformations. But in biology, that's what they use for the Hallworth, and then they show straight up and down lines to indicate whether it's above or below the plane of the ring. Again, when you get to organic, you now know that that's a chair cyclohexane. So for sugars then, sugars can exist in a open chain form where they're an aldehyde, or in a closed chain form where they are hemiacetals. And when you dissolve glucose in water, I think 99% of it is in the ring form, in that ring form, and only less than 1% is in the open chain form. And then with fructose, you're actually reacting the OH in red on carbon 5 with the carbonyl on carbon 2 with the ketone. And so you're actually making a 5-membered ring. And then if you take the glucose and the fructose and take 2 of those OH groups and bring them together to make an ether, you make sucrose. So sucrose is glucose and fructose together. And fructose is one of those sugars that is like low glycemic index, so it won't raise your blood sugar. But then again, it's not good to be eating a lot of that kind of sugar. So these are all cyclic hemiacetals, or in the case of fructose, acyclic hemiketal. And so you've seen those structures before. And so here I think this slide says that you've got less than 1% open chain, and then depending on where the OH group on the far right is, whether it's below or above the plane of the ring, that gives you two what are called anomers, and then that's the alpha and the beta terminology. So if you've talked about carbohydrates, then you've talked about the alpha and the beta, and one of these reacts far faster than the other. And basically these are two diastereomers if we want to go back to last semester, because changing the configuration on the OH on the far right is just changing one chiral center, and so these are two diastereomers and one reacts much faster than another. And that's actually called the anomeric effect with carbohydrates. And then if you take the carbohydrate rings and you put them together, you make cellulose. So if nothing else, in a general biology class, you've seen cellulose. That is a bunch of cyclic hemiacetals linked together as ethers. Right? So that would be the organic description of cellulose, which you usually talk about in general biology long before you get to organic. And so then you see these flat rings that are nonsense. So that's where the cyclic forms come from. So that's where the sugars and carbohydrates are formed, and the cyclic form is more stable than the other. That's why when they get in the ring, get in water, they form those ring forms. Now we'll come back here to the cyclic acetals and ketones maybe today, but a couple more reactions I want to talk about. And that is now, so we've done OH, or we've done water, and we've done alcohols. The next group, let's go ahead and add, are amines. Okay. And amines can have 3 hydrogens, in which case it's ammonia, or 1 hydrogen and 2 R groups, which is called a secondary amine. Or you can add an amine with 2 hydrogens in an R group, which is a primary amine. And then a nitrogen with 3 R groups on it is called a tertiary amine. And that can't react. And then if you put 4 R groups on it, then you end up with an N+, and having 4 R groups on the nitrogen with the plus charge is number 10 on the chart. Although it could very easily be 3 hydrogens as well, because the ring counts as one connection. So as long as it's got 4 things attached to the nitrogen with a positive charge, that's number 10. Okay, that's the most deactivated, and in most textbooks that will not react in electrophilic aromatic substitution. Okay. So there's 2 different mechanisms for adding a primary and a secondary amine to the aldehyde. Primaries go by one mechanism and form one compound. Secondaries react by a slightly different mechanism to form a second compound. The key thing with amines is that you do not need acid. Amines on the periodic table, nitrogen is a stronger base than oxygen, which means that it is a stronger nucleophile than oxygen. So nitrogen does not need H+. As a matter of fact, if you add H+, when you're trying to do this amine reaction, what will happen is that if I took my aldehyde and I said, I'm going to react that with H+, And an amine, the amine being the stronger base, would end up being protonated, so that I would end up with my carbonyl with my now 3 H's on the end with the R group, the plus charge. An amine with a plus charge is no longer a nucleophile. So if you added H plus thinking that you were going to make the reaction go faster, you would kill it. Because now the nitrogen is not a nucleophile, it's an electrophile, and so it can't add to the carbonyl. So that means no H plus for amines. Just take the amine, add it to the carbonyl. Okay? So that's what we're going to do. So let's take that same aldehyde, and now let's add it to a primary amine. So NH2. What's going to happen in the first step of this mechanism?
Element.
All I've done is I've replaced the water or the alcohol with the amine. And I don't have any acid. So what's the amine going to do? What did the water do? What did the alcohol do with the carbonyl? It don't need any protonation. So this is my delta positive carbon. This is my delta minus nitrogen. This is going to attack the carbonyl, and the pair of electrons is going to go up there. So the nitrogen is going to attack the carbonyl, and it is strong enough that it does not need any acid help. Like I said, acid will kill this. So my nitrogen is going to add to my carbonyl, and it's going to form this, where there's an O minus and an N plus, and an N plus. Now what's going to happen next? The O minus is a strong base. The nitrogen is a decent acid. So what's going to happen is that the O minus is going to deprotonate the NH plus. For the sake of paper, I'm going to take this O minus and I'm going to say, you know what, it's just going to come down and grab the H plus. Is that what happens? I doubt it. So why did you do it? So I didn't have to write 2 molecules. What most likely happens here is I don't think there's enough, I don't think the spacing is enough so that the O minus is going to be able to get close enough to that NH plus in the same molecule to be protonated. But remember, one of the issues in doing mechanisms on paper is that we are doing one individual molecule, and what we have to remember is there's billions of molecules in this solution. So what most likely happens is the O minus of one takes the NH plus off another molecule. So it's more likely an intermolecular process than intra, but most textbooks show this as some sort of intramolecular proton transfer, which I doubt. But we can do it. So now I just made this molecule. Now one of the things that I should probably add to this is that we normally use heat for this reaction. And so here's what's going to happen in the heat. This pair of electrons on the nitrogen, the NH bond is going to go there to form a CN double bond. Now at the same time, you would say, oh, I'm going to lose OH. So that what I'm going to end up doing is I'm going to end up forming a C double bond N the N still has the R group, and I will make water. Now, if anybody's exercised about the fact that I just lost an OH group as an OH group, it doesn't sit well with me either. Except I can sort of make up stuff and say, oh, well, this is heat. So I can kick the OH group because I'm applying heat to the system. And what I actually suspect happens is that this is one of those things where two molecules again come together. So that what's happening is as the OH group comes off, there's a nitrogen with a hydrogen ready to protonate it and let it go. So are we really losing OH as OH minus? Probably not. So it's probably picking up the hydrogen as it leaves from the nitrogen of another molecule. But this is what happens. So we make this molecule, which is called one of two things. This technically is a Schiff base if the R group is not hydrogen. So it's a Schiff base if R does not equal hydrogen. If R equals hydrogen, then that means it came from ammonia to begin with, and that is called an imine. So technically, the NH group is an imine, while the NR group is called a Schiff base. The whole thing. So the whole thing with an NH is an imine. The whole thing with an NR group is a Schiff base. Yes. Yes. This is what we're talking about. So that's technically, this one is technically a Schiff base. But if I started with NH3, it would be an imine. I use the two terms interchangeably. So I'll sometimes call them imines, I'll sometimes call them Schiff bases. But that's the mechanism for a primary amine. You make the Schiff base amine. So this is called addition-elimination. So in the first step, I'm doing addition, and in the second step, I'm doing elimination. So most textbooks will call this the addition-elimination reaction of amines and ketones and aldehydes. So this is how we form the Schiff base, or the imine. And what do you do with these things? I won't go into it. But they have some, depending on what the structure is, they have some interesting uses. I know we were trying to make, I wasn't trying to make, one of my colleagues that was here like 8 years ago, she was trying to make this, one of these compounds, and couldn't get it to eliminate at all. And so every time they tried the reaction, they ended up with this brown gooey stuff. Then I stupidly said, well, you know, you can use my lab and try it there, and then all of a sudden the hood's filled with brown bottoms full of brown gooey stuff. But this was even gooier. So the thing was, it wasn't working. So then we took then I unfortunately got involved, and we then tried to sort of we then tried to use like ether as the solvent. We ended up making these really nice yellow crystals. I sent them down to the guy that was at Youngstown State. He did a diffraction analysis, and it came back, it was half amine, half OH, which most books don't tell you what that is. That is called now I'm going to forget what it's called. It's called an aminal, right? Sort of like a ketal, but with the amine, it's called an aminal. So they couldn't actually get the structure of it, but when he sent it back, he goes, here's what I got, and I go, oh, I know what that is. But we couldn't get it to dehydrate still until we did this reaction with copper metal. And this was supposed to work from some Iranian chemist who said, oh, well, you can make this stuff all day long, and we couldn't. Still can't. But when you put a metal in there, what it does is it brings the two pieces together, and then it forms the imine. The only problem is the metal's still in there, and you can't get rid of the metal. And I never did know what to do with it until somebody made something very similar, and they were using it to nick DNA. In other words, to go into DNA in the interpolation sites and do reactions with DNA. So we still have to publish that structure, but these Chinese researchers that did that, like, there's only 2 atoms difference. But we have a way we can make these things all day long if you just throw copper in it. So, looks easy on paper, not so much. Primary amines to make shift bases. And most people who are making shift bases are putting metals in there to bring the molecules together, and then that forces them to dehydrate. Again, that's the role of metals in organic synthesis that we don't get from the first 2 semesters of organic. I digress. What happens if I react a secondary amine? If I react a secondary amine, let me change the structure here. Let me put in that CH2 group because that's going to become important. What's my first step going to be? The amine's going to attack the carbonyl group. I'm going to make the O-, and then my nitrogen's going to have 2 R groups and an H off of it, but it's still going to form the ammonium. So now what's going to happen? So we'll have this non-existent intramolecular hydrogen transfer. It really doesn't exist, but we'll say it exists. Okay, so we're going to make that. Now, my final step, this is still addition-elimination. All right, so the problem here is if I'm going to do my elimination and lose water, there's no more hydrogens on the nitrogen. In a primary amine, when you had 2 hydrogens, the first one got lost to the O-, but there was still 1 more left. In this case, with a secondary amine, there's no more left. No. They're all equilibrium steps. So there's no hydrogen on the nitrogen to be lost to form water, and I'm still applying heat here. But there is a hydrogen on the carbon that's attached to the carbonyl. And so under the heat, I can now lose water this way. So lose it from the carbon that's attached to the carbonyl. And now I'm going to end up with now a double bond on the carbon-carbon bond, and then the NR2 group. Now this is called an amine. It's an enamine. Why is it called an enamine? Because it's half alkene, half amine. I would ask, what does it look like from before? What have we looked at that was half alkene and half something else? The enol. So if you have an OH group there, it's an enol. If you have a nitrogen, it's an enamine. So primary and secondary amines do two different mechanisms to form two different compounds. What do you do with an enamine? The same thing you would do with actually what's called an enolate, which is a deprotonated enol, last chapter. So we'll come back to enamines. But this is how you make them. Okay. So those two reactions are different. And these can be done with ketone, or it can be done with an aldehyde. So all these mechanisms, if I replace the H with another R group, I would get that product. Okay. What other reactions do we have of ketones and aldehydes? Well, these are the addition reactions. We have additions to form acetals, hydrates, hemiacetals. We now have addition-elimination to form amines and enamines. The rest of the reactions of aldehydes and ketones are just kind of reactions, one-shot reactions. One that may not seem like it's all that useful is to take a ketone and react it with our friend the peroxy acid. And so we have to remember, what does a peroxy acid do? It makes an epoxide with a double bond, and in making the epoxide with the double bond, it takes and basically puts an oxygen above both, attaches the oxygen to both carbons in the double bond. The key thing is that the peroxy acid adds an oxygen atom. So in this case, what does a peroxy acid do? It's going to insert an oxygen between the carbonyl and one of the R groups. So I'm going to end up forming an ester. So using a peroxy acid with a ketone is going to make an ester. And this is actually called a Baeyer-Villiger reaction. There's probably two questions that come to mind. Number 1. Anybody have a question? Yeah. That's the first question. So if we had something like an ethyl group on one side and a methyl group on the other, and we added the peroxy acid, where would the oxygen go? And the answer is that the oxygen is going to go on the side of the larger, it's going to add the larger R group. And we're not going to do the mechanism of this, but the mechanism tells you that it will go, the O will go on the, in between the carbonyl and the larger alkyl group. So that's the first question, is where should the O go? It should go between carbonyl and the larger alkyl group. The second question might be, who cares? And the short answer to that is you for the next 2 weeks. Then after that, you're on your own. It's a Bayer-Villiger. Or Bayer-Villiger. Right. Right. Same thing. I'm not sure. I'm not sure. You can Google it after class. Notice I said after class and not during class. Who cares? People that want to make cyclic esters. If you wanted to make an ester that looked like that, cyclic esters have their own name. They are called lactones. So a lactone is a cyclic ester. And how are you going to make that cyclic ester? Well, you might say, let's do Fischer esterification. Let's take a carboxylic acid on one end of the molecule and an OH over here on this end of the molecule, and then hope that the OH on the one molecule wraps around and adds to the carboxylic acid at the other end. So that's one way to make lactones, except that's not going to be tremendously efficient, because that OH on the one end might react with the carboxylic acid on another molecule, so that you'll end up making a chain of esters, which would become a polyester, and you don't cyclize it. So the nice thing about this Bayer-Villiger reaction, and if they did win the Nobel Prize, they would have won it, because if we take a 5-membered ring ketone and we treat it with the peroxy acid, we immediately put the oxygen into the ring. So we don't have to worry about the OH on one end of the molecule wrapping around and adding to the other. So that would be a really useful thing to have to make cyclic esters called lactones, and lactones can be added on to make all sorts of bio-related molecules. So that's where they're most useful. So that's one of the kind of different reactions, is Bayer-Villiger. Another reaction of aldehydes and ketones only occurs with aldehydes. And that is, how can we oxidize just aldehydes? So aldehydes can be oxidized specifically in two ways. One is to use silver metal hydroxide, and we also use ammonia. This is called the Tollens reagent. And so Tollens reagent of silver, hydroxide, and ammonia only reacts with aldehydes. It won't react with alcohols. It won't react with anything else but aldehydes. And it's going to oxidize that aldehyde to a carboxylic acid. Since this is in basic solution, the carboxylic acid is going to be deprotonated. And that's great, but it's boring. What's the important part of the Tollens reagent is what happens to the silver. And so the silver ion then becomes silver metal. And so there's a video within the lecture, and then there's a standalone video link for this Tollens test or Tollens reagent, that if you take, and usually what we use is a sugar, because this will react with that 1% of the open-chained sugar. You take a little glucose, you take the Tollens reagent, put it in a flask, swirl it around, it makes the silver metal. The silver metal adheres to the inside of the flask, and you'll end up basically mirroring the inside of the flask. Right, so it'll look like a Christmas ornament. That's a Tollens use. And this would have been a useful reaction to make mirrors in the old days. Right, so in the old days, when you see a mirror, an old mirror that's looking like it's tarnishing, that's because the mirror is silver. So it's tarnishing just like silverware. And one of the ways that you could have made that mirror was by using sugar and this set of reagents in order to coat the glass. And then let's see. Usually I can't quite figure out. So you have to shoot werewolves with silver bullets, right? Because like vampires, you use the wooden stake. But vampires, you don't shoot with silver bullets. That's only werewolves, I think. But for some reason, the reason that vampires cannot see themselves in mirrors is because this is the old mirrors that were made of silver. So I don't quite understand how that works, but I don't know. I know you kill werewolves. I don't know if werewolves, if they can see themselves in a mirror or not. Well, that's what you use silver for, right?
But then they should be able to see themselves in mirrors.
Well, that's the conundrum here. If you had a vampire that's living today, and most mirrors are made actually using molten zinc. So today's mirrors are made from zinc, not silver. They should be able to see themselves. I mean, this is one of those. No, I think if you put the wooden stake through their heart, they die.
I just told you back here.
So anyway, I don't know anything about zombies. So anyway, this is how we used to make the old mirrors, is with Tollens. So there's a second reaction called the Benedict's reaction. And if you've taken like general biology, you may have actually done this reaction. So in the Benedict's reagent, you react an aldehyde, and again, this only works with aldehydes. You react it with copper ion in base. And the aldehyde gets oxidized to the carboxylic acid, but it's in basic condition, so it's deprotonated. And now the copper ends up going from copper 2 to copper 1, which means it makes Cu2O, which is copper 1 oxide. And so copper 1 oxide precipitates from the solution. Again, the oxidation of the aldehyde isn't as spectacular as what happens with the copper oxide. So copper oxide then has a brick red color. And it's brick red because it's the metal they put in bricks to make them red. So what happens is you take your solution, and copper 2 solution is, anybody know what color that is? No. Blue. It's the good shade of blue. It tends to be the darker good shade of blue. So copper 2, what happens is, if this is a test, the Benedict reagent is used to test for what is called reducing sugars. So if you've ever in your biology class taken a sugar, added it to a test tube, and then added copper hydroxide and heated it with a Bunsen burner, and it changed colors and turned red, then that's a positive test for reducing sugar. So if you did this with again glucose, which is in its 1% in its open chain form, with an aldehyde, it will react. If you tried to do this with sucrose, which has the two closed chains forms of glucose and fructose, it will not react because there's no free aldehyde in solution. And then allegedly you can do this with other sugars and it'll change other colors depending on what the sugar is. And you can use this type of reaction to determine what your sugar is, what kind of sugar you have. So both of these are color tests for aldehydes. And in the old days, before we had spectrometers, and somebody gave you a molecule and you thought it was an aldehyde, you would have to do these tests because they would be a positive test for an aldehyde. Okay, so I will send out tonight, tomorrow, a list adding on these reagents, adding on these reactions for Monday's test. Sadly, going into today, we only had one mechanism, I believe, that we could have done on Monday. Now we've added a couple more. So Monday, I'll give you the list for Monday of topics. If you have any questions, send me an email. Keep remembering your chart and this new stuff.